Hello, everyone. My name is Siyang Ling. I'm a postdoc at the City University of Hong Kong, and today I'm going to talk about a recent work with Mustafa Amin on simulating free streaming in warm wave dark matter. So here's a table of contents. Let me start with free streaming of wave dark matter. So you probably heard of the usual story of wave dark matter. Depending on the context, people call it fuzzy dark matter, ultralight dark matter, XL-like particles, and so on. So one prediction that people make for wave dark matter is the matter power spectrum. And when you look at how people do these predictions, you'll find that they usually assume a large zero mode or homogeneous mode for the wave dark matter field. And with this zero mode, they can linearize the field equation like this by breaking the field phi into phi bar plus delta phi, where delta phi is the inhomogeneous part. And then they can do a Fourier transform and get the mode equations for each wave number phi. And if they just put this equation into software like Axion Cam or Class, they can evolve the dark matter field from the primordial initial conditions to late time predictions for the matter power spectrum. So now my question is, what happens if you don't have a homogeneous mode? Now, still, let's think about a free field phi. Its energy density will be something like m squared phi squared. Its momentum density will be something like phi dot gradient of phi. Suppose if you have a large homogeneous mode, then you can linearize with respect to phi bar, and your inhomogeneous part delta phi will be much smaller than phi bar. But this approximation is not valid in the case when you don't have a homogeneous mode. When we look at density fluctuations, we'll find that delta rho for the large homogeneous mode case will be something like m squared phi bar delta phi. So basically, we can linearize the density fluctuations also, and delta rho would be proportional to delta phi, and delta rho would be much smaller than rho bar, the typical value, the average value for the energy density. However, if there's no homogeneous mode, then delta rho would actually be comparable to rho bar. A similar thing happens for the momentum density Q. So if you have a large homogeneous mode, then your momentum density will be order phi dot gradient of delta phi. Notice that the homogeneous part phi bar gets hit by the gradient and it just becomes zero. That means your momentum density will be much smaller than the order of this quantity, k star phi dot phi. Where here, k star is the characteristic wave number of the field phi. However, if you just try to calculate the same thing for if there's no homogeneous mode, then your momentum density will be order k star phi dot phi. So the gist is that if you don't have a homogeneous mode, then you will have large density fluctuations and large momentum densities compared to the case when you have a homogeneous mode. So how does this discussion manifest itself on the matter power spectrum? So having large density perturbations means that you're going to get some large peak of the matter power spectrum at small scales. Here, I take an example for which k star is around 10 to the 3 megaparsec inverse. And you can see that the power spectrum, with the matter power spectrum, will have a peak with amplitude around order 1. That is a consequence of the field having delta rho, the energy perturbation in energy density, delta rho, to be comparable with rho bar. And just below that k star, you get some k to the 3 power law in the matter power spectrum, the white noise spectrum. And all of this, the white noise and the peak, collectively, we usually call it isocurvature perturbations or Poisson fluctuations. And these fluctuations on the matter power spectrum are due to the small scale field fluctuations. And what about the large momentum densities? Now, since now we have large momentum densities, the wave packets in the field phi will be moving much faster. Basically, they will move with typical velocity k star over m. And that means we're going to have free streaming suppression of the matter power spectrum over time. And that is another effect that we could potentially see on the matter power spectrum. And thirdly, the matter power spectrum has to, since we are still talking about a dark matter field, the matter power spectrum still inherits adiabatic initial conditions. And these adiabatic initial conditions will eventually get suppressed by the free streaming. This has been pointed out by Mustafa Amin and Merida Marbabani in their PRL paper. Now let me show you some pictures to give you a better intuitive understanding of the physics here. Suppose our dark matter field phi has power spectrum p phi, and you generate some statistically homogeneous Gaussian random field, then the realization phi will look like the blue curve on the top panel here. You can clearly see that there are much small scale fluctuations of length scale 1 over k star, but the field is still statistically homogeneous, meaning that if you take phi squared and you take the ensemble average, what you'll get is just a constant over space, as shown by this orange curve here. If you think about it, this means at large scales, there is no density fluctuations for the field phi. But that's not what we want, because our dark matter field phi will inherit adiabatic initial conditions, and we will have to somehow incorporate that. The way we do it is to drop the statistically homogeneous assumption and make the variance of the field inhomogeneous. The bottom plot is one example of such fields. You can clearly see that the variance in the middle is much bigger than the variance on the sides. And if you calculate the density spectrum from such a field, you will get contribution from the small scale isocurvature perturbations and large scale perturbation due to the inhomogeneous variance. And that's how you get both a plateau on the large scale here and a peak at the small scale here. These contributions are from the same field. And how does free streaming manifest itself at the field level? You can think of the field as composed of wave packets moving at random velocities. And the wave packets this movement of the wave packets will be completely stochastic. But on a macroscopic scale, what you see is the diffusion of the initial overdensities. Basically, after the wave packets have moved for over some distance, you don't know their positions anymore. So their variance will just tend to a spatial constant. And to talk about free streaming, of course, we want the free streaming length. To calculate that, we just treat the wave packets as particles of mass m and co-moving momentum q. And in radiation domination, you can just calculate this length by doing this integral, which is just velocity times time. And what you get is basically that the free streaming length grows logarithmically in the scale factor. So on the power spectrum, free streaming will tend to wipe out long or large scale perturbations over time. By long perturbations, I mean the perturbations that are not isocurvature perturbations, and they are of length scale shorter than the free streaming length. The short isocurvature perturbations are not affected by free streaming. So on the figure below here, I show you the density spectrum from an actual simulation. You can see on the gray curve here, there's initially some large-scale density perturbations, but after field evolution, they get suppressed due to free streaming. The isocurvature perturbation at the peak here remains unchanged. And all of these have been observed by Mustafa Amin and Merida Marbabani. They argued for the time dependence of the overdensity spectrum, and that result is given by this equation. And from this observation, they got a mass lower bound for ultralight dark matter with Lyman alpha data. the bound is 10 to the minus 18 electron volts. So what's new about our work? Our work is about getting a framework to use lattice simulation to study free streaming in precision. Now, to do an accurate lattice simulation of free streaming, the hard part is actually to prepare the right field initial conditions. So here I list some features of the field initial condition that we want. Suppose our dark matter field is produced post-inflationary by causal and subhorizon production mechanisms. It will have no field zero mode. Its spectrum is something that we can set, will be peaked at some k star, and the field should inherit the large-scale density fluctuations from adiabatic perturbations. So now let's look at the spectrum. In our paper, we choose this simple broken power law parameterization for the field spectrum. You can see it peaks at k star, and below k star, it has power law nu, and beyond k star, it has power law alpha. And now let's look at the density spectrum. The peak of the density spectrum is given by the isocurvature perturbations, which means it's determined by the field spectrum. And since the field spectrum peaks at k star, the density spectrum will also be peaked at k star. Just below k star, you get some k to the 3 power law, a white noise spectrum. You can see this white noise is a pretty generic feature of many different choices of nu and alpha, different choices of the field spectrum. You can kind of argue that the density, this is due to the finite correlation length of the density perturbations. And at even lower k, you get a scale invariant k to the 0 spectrum, and that is something I put in by hand to reflect the adiabatic initial conditions. So how do we generate a lattice realization that ensures adiabatic initial conditions? Suppose we are given a gravitational potential psi at some point. The adiabatic initial condition says that our field phi, if you use it to calculate delta, the overdensities, you should get you should be able to get these relations. It should satisfy these adiabatic initial conditions. So how do we do that? Remember now our field phi don't have a zero mode, so you cannot do it by simply doing something clever with delta phi, because delta phi is phi bar is now 0. You cannot say set delta x is equal to proportional to delta phi or something. So how do we do it? The way to do it is to consider an ensemble that captures the randomness of the small scale fluctuations. Let's think about when you evaluate the overdensity delta x at some fixed position. If you calculate it for some given field realization, the value of delta will be dominated by the isocurvature perturbations. Now we want to get rid of this isocurvature perturbation. So we take an ensemble average, and we say that after ensemble averaging, the overdensity should be equal to the density perturbation given by the adiabatic initial condition. And if you enforce these two relations, but that's given for delta and delta dot, that's purely just from adiabatic initial conditions, you would get that the field will have inhomogeneous variances, as I said before. And in fact, you can calculate the how inhomogeneous the field variances are, and it's given by these functions f1 and f2. You can see f1 and f2 are proportional to psi, the gravitational potential, and W here is the equation of state of the field. Now, in the end, we still need an algorithm to actually generate the lattice realization on the computer. So basically, we found an algorithm to do to generate this inhomogeneous Gaussian random field. I'm not going to go into the details, but basically, if you define the phi hat to with this relation, the phi hat to be Gaussian random variables that satisfy this relation on the right, and then you multiply phi hat by this spectrum in Fourier space, the phi that you get is exactly the field that you want. If you have an inhomogeneous variance and if you have the right spectrum. The blue curve in the bottom here is generated by this algorithm. Now let me show you the results from my lattice simulations. The first result is a Klein-Gordon field in a radiation-dominated universe. It has Hubble expansion, and there is this external gravitational potential psi that evolves according to this formula. And the adiabatic initial condition is set to in the initial condition of the field. Now, let me show you the evolution of the field in terms of this video. So initially, you can clearly see a significant growth in the large-scale density perturbations in the field. That is the Hu-Sugiyama growth. And if you look closely, you also see some free streaming suppression at around k to the 10 to the minus 1 here. And after some time, you don't see the density spectrum changing all that much anymore. That's because the free streaming length depends logarithmically in time. So things are moving very slowly. So let's suppose but now let's accelerate the time to much later times. Then now you're going to see significant free streaming suppression in the density spectrum and in the snapshot on the right panel here. So we also extracted the free streaming length from our simulation by some fitting. And we compared it with our theoretical predictions for the free streaming length. And as predicted, the free streaming length grows logarithmically in the scale factor. However, the predicted free streaming length is longer than in the simulation by a constant. This difference is resolved by changing how we calculate, changing the start time of the free streaming. Intuitively, this makes sense because free streaming can only happen after the initial density perturbations have grown. The other lattice simulation result that we have is for a field with strong nonlinear self-interactions. The equation is given by this. The field is in a Minkowski background with this nonlinear potential called the monodromy potential. And again, let me show you the evolution of the field by this video. Initially, you can see that there's large-scale density fluctuations here and there. And when you evolve the field, you can now see lots of small orange blobs forming, and those are the solitons due to the nonlinear self-interaction. You can see that they're mostly forming in the initially dense regions, but not that much in the initially less dense regions. And in the density spectrum, you can see a new peak forming, and that corresponds to the soliton scale. When you continue to evolve it, you can see there is suppression in the large-scale density perturbation here. And that is also reflected in the snapshot on the right here. So initially, the solitons were all clustered around the dense regions, but after evolution, after the solitons have moved around, now you don't really see a particular location preference for the solitons. So the conclusion is that free streaming, in this case with nonlinear self-interactions, also takes place. So to summarize, we have provided the framework for simulating wave dark matter free streaming. The hard part is about how to set up initial conditions for the simulations, and we also have a code base for simulating the field. And we have done the simulation for a free field in radiation domination, and we have done the simulation for soliton forming strongly self-interacting fields. That's all. If you're interested, you can check out our code base, Cosmic Field Lite.